Factoring in order to solve equations, and what we'd like to do today is to turn to inequalities and see if we can't utilize the same idea. Okay, and before we do so, there are two statements which turn out to be quite important, which in fact we may even call theorems. And for every a and b belonging to the set of real numbers, a times b is greater than 0, all right, is greater than 0 if and only if. And let's see now what we may say. The fact that the product of two numbers is greater than 0, you would like to say what? That a is greater than 0, and what other conclusion may we come to? Must we come to? And what? Can anyone think of something, Steve?
B is greater than 0.
And b is greater than 0. Or we may have what? A is less than 0, and then of course that forces you into also concluding, Steve, that b must be less than 0. All right? Now, there's a second theorem which we may state. I'm not going to prove these, but rather simply utilize them. For every a and b belonging to the set of real numbers, a times b is less than 0 if and only if, all right? If and only if, and now what do you think we might say? A is greater than 0, and now what position are we forced into, Doug?
B is less than 0.
B is less than 0. Or, now notice all of our algebra here, or our logic here, a is less than 0, and what then must we conclude but that, Bill?
B is greater than 0.
And b is then greater than 0. All right? Now, from these two statements, I think we can go ahead and look at some quadratic inequalities, if you will, and in fact, as you do some of these problems for homework, you'll even be able to do some problems that have to do with a third-degree polynomial inequality. Now, let me also say that later on, we're going to look at these same ideas from a graphical point of view, making graphs, and I think, in fact, it's going to be a lot easier when we make graphs and look at our x-axis, say, and come to some conclusion. But right now, this is purely an algebraic approach that we're going to be doing as we solve these problems. Well, let's look at an example of these theorems. Well, suppose we have, say, x minus 2 times x plus 3 is greater than 0, okay? And again, right here, you say to yourself, I have a times b is greater than 0, and then let's simply apply our theorem. Therefore, x minus 2 is greater than 0, and x plus 3 is greater than 0, or, let me indicate it in this fashion, or, what else do we want to say? X minus 2 is what? Less than 0, and x plus 3 is less than 0. Well, let's then continue this vertically here. Let's come back to this line, and therefore what can we say but that x is greater than 2, and x is greater than what number? Right here, negative 3, or, all right, let's then look at this line. We have here what? X is less than 2, and what other conclusion may we come to? X is what? Is what? Less than negative 3, okay? Therefore, now let's look at this line and see what we may say. We're interested in all those real numbers x such that x is both greater than 2 and greater than negative 3. So what set of numbers will satisfy both of those? Just think of the number line, Doug.
All x such that x is greater than 2.
All right. All of those values of x such that x is greater than 2. Let's write this using our set bracket notation. The set of all x's such that x then is greater than, what? Greater than, from this sentence here, greater than 2. Is that right? All right. Or, now let me use, since we are talking about sets, let me introduce our union symbol. Or, and now let's look at this sentence and see what conclusion we may come to. We're interested in the set of all x's such that x is less than 2 and x is less than negative 3. So what numbers will make that sentence true, Tim?
X is less than negative 3.
X then is less than negative 3. The set of all x's such that x is less than negative 3. Now, looking at the union of these two sets, I think you would say then our final conclusion is what? The set of all x's such that, and now let's try to put it into one set notation. We're interested in all of those numbers such that all real numbers, such that x is greater than 2, or x is what? Less than negative 3. Is that right? X then is greater than 2. What word do I want to use here? Or x is less than negative 3. And then if we were to make the graph of that sentence, let's see what it would look like. Suppose this is 0, 1, 2, 3, 4. And to the left, 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. We're interested in those values such that x is greater than 2 is an open circle. And what then do we want to say to the right? But a what? A solid line. And to the right, is that right? Okay. And then we are interested in those values such that x is less than negative 3. Here's negative 3, and our arrow is to the left. And that then is the graph of this solution set. All right? Let's look at another example. And suppose we had a problem such that, suppose we had x squared plus x is less than or equal to 12. And notice now it's not quite in the pattern that we would like to see it in. We want it in terms of less than or equal to 0. So what then may we write here for another sentence? And Don?
X squared.
X squared
Plus x.
Minus 12
Is less than or equal to 0.
is less than or equal to 0. Notice now in this case also we're talking about less than or equal to. And we talked about the case of equality in our last lesson, so perhaps we can simply continue with the inequality symbol, with the less than or equal to symbol all the way through. Now, again, looking at our left-hand side here, you would like to factor it, and Doug, it factors into
X minus
x minus 3
X
times
plus 4.
an x plus 4. Does everyone agree with that? Is then going to give us a negative 12 and a positive 1 times x here. Notice now we're talking about less than or equal to. Therefore, what can we say but that x minus 3 is what? Less than or equal to 0, and what must we say? X plus 4 is, well, if this is less than or equal to 0, this one then must be greater than or equal to 0. Utilizing our theorem in number 2 over there, is that right? We then have to conclude that what this one say is negative, therefore this one must be positive, or, now if this one then were, say, positive, therefore what? And our conclusion must be that what? X plus 4 must be less than or equal to 0. Therefore, now let's then come back to this line again. We have there what? X then is less than or equal to 3. And here we may say what? X then is greater than or equal to what? Negative 4. Or, now let's look at this line. We have what? X then is greater than or equal to 3. And x then is less than or equal to negative 4. All right? Therefore, now let's then go right to our set notation. X is less than or equal to 3, and x then is greater than or equal to negative 4. I think you will agree we may say is a set of all x's such that, and may we write this in a slightly different pattern with the number x between something, and between what two numbers? Between what? Negative 4 on the left, is that right? X then is greater than or equal to negative 4, and x is less than or equal to 3 will be this statement. And then we are interested in union, and now let's look at x is greater than or equal to 3, and x is less than or equal to negative 4. What numbers will make that sentence true? What may we say about that? Is there any number that you can think of which is greater than or equal to 3, and at the same time less than or equal to negative 4? What's your conclusion? Union what? Union the empty set. Now, this sentence, union, or this set, union the empty set, then is going to be equal to simply this set. Is that right? So we have the set of all x's such that, let's continue with the same notation, such that it then is between negative 4 and 3. That then is our solution set, and the graph of that solution set, you know, we may make in terms of 3, 4, and so on. And then 1, 2, 3, 4, say to the left, negative 1, negative 2, negative 3, negative 4. It then is going to be what? The fact that it's less than or equal to, or in this case greater than or equal to, it's going to be what? A closed circle. And on the number 3, it's going to be a closed circle, and what then is our conclusion, but that we want what? Everything in between, is that right? It's then all numbers between those 2 points, and that's the graph. Well, this is a relatively short lesson, so let me give you your homework assignment. This will be a